All right, so our last section we'll look at today is the same section. It's just part 3, and we're going to look at what's called a period change. So this is the fourth and last transformation that we'll do. All right, so first thing I'm going to show you is what a period change looks like as an equation. Okay, just to summarize, we had phase shift. That involved adding or subtracting inside the parentheses. We had vertical shift. That also involved adding or subtracting, but it was outside the parenthesis. When we did amplitude change, that involved multiplying in front of the trig function. Well, this transformation also involves multiplying, but it's inside the trig function. So when you multiply inside the trig function, that's a period change. So the letter that your book uses, you can really put any letter you want in front of X. They just use this Greek letter. Kind of looks like a W, but it overlaps a little in the middle. And that just stands for a number. Okay? Could be, in this case, 4 or a 2, but that number controls how the period is going to change. Okay. The way you can think of a period change is you are stretching or compressing the graph, but we're not doing it vertically. We're doing it horizontally. A couple of the examples I have right here will cause the graph to compress. There's another one up here that will cause it to stretch. And we have to remember that there's 2 transformations that do the opposite of what we would expect, and there's 2 that do what we would expect. The ones we did yesterday were what you would expect. When you put a plus on the end of a number, it did shift up. When you did minus, it shifted down. So there's one that does what you expect, and amplitude change also did what you would expect. If you put a big number in front, stretch the graph bigger. Put a fraction like 1/5 in front, it compressed it smaller. So we've already done both transformations that would do what you would expect. So that means this transformation is going to do the opposite. Okay? It's not going to be what you would expect. So this graph on the calculator, just sine of x and sine of 4x. Okay, so at first you might think, well, if you put a 4 is a number bigger than 1. It's going to stretch the graph bigger, but it doesn't work that way. The bigger the number you put in front of the x, the more compressed it's going to get. Okay, that's the original, and that's sine 4x. Okay, it's actually been compressed 4 times as much as the original. So let me just make that a little bigger. All right, so if you focus on, just focus on one section of it, like of the blue wave, from here to there. If you look at the blue wave, it goes up, down, back up, 1 time. Okay. Now look at the red wave. Up, down, back up, it's 1, 2, 3, 4. That's where the 4 comes from. So for every 1 cycle you're getting in blue, you're now getting 4 cycles in red because you've compressed it. So the bigger the number, the more it compresses. If you make the number smaller, okay, like let's put in 0.5x, what do you think a number less than 1 is going to cause the graph to do? Yeah, it's going to get bigger. It's going to stretch out. Okay, so there's the original. And now here's the one in red. It's been stretched out. So now, in order to get a full cycle of the one in red, you have to go twice as long as the one in blue. Okay. You kind of just focus on here and here. Okay. Get 1 cycle, 2 cycles. All right. So that's the effect of changing the number in front. So we're stretching and compressing along x-axis. And for this particular transformation, I'm only going to give you positive numbers in front of x. Could this be like a -4 or a -2? Absolutely. It would cause a flip, okay, to happen. So we talked about a flip with the amplitude change, flipped it vertically. Well, a negative in front of the x here would cause a flip horizontally. But we're just going to stick with positive numbers. So if the number in front of x is greater than 1, it will compress. How much? It'll compress by a factor of the number. If it's a 10, it's a compression 10 times as much. If it's 1,000, it would compress 1,000 times as much. If the number in front of x is between a 0 and a 1, then it will stretch. How much will it stretch? Well, it stretches by the reciprocal of the number. So if you put a 1/2 in front, 1/2 will stretch it double. If you put a 1/3, it would stretch it triple. 1/5, stretch it 5 times as much. Okay, so any questions on what a period change looks like, what it does, and specifically what kind of number causes it to do one thing, and then what kind of number causes it to do the other thing? All right, so I'm going to go back to that sound that I said I was playing when you guys walked in. Did anybody hear a sound for it was probably like 10 minutes or so while I was checking homework? If you heard it, you probably wouldn't have liked it. It wouldn't have been a very pleasant sound to listen to. And you might ask me, well, how do we even know you were playing a sound? Well, I can show you, prove to you I am. So what now you're seeing a graph of all the frequencies in the room. It's also showing how loud the frequencies are by the height. But if you look left and right, like when I speak, you see movement probably all the way up to around 12,000 hertz. So there's some really, really high-pitched frequencies in my voice that are very, very soft, but you don't really hear them. Most of the frequencies in my voice are probably under 1,000 hertz, maybe in the 200 to 600 hertz range, so it's relatively low frequency. But if you were to whistle, what I can do is you'll see a spike at one point, because at that point I'm just making a constant frequency sound. So if I do that, actually you saw like 5 or 6 of them. So even though I was trying to just make a single sound, apparently when I whistle, it's looked like it was a bunch of frequencies. But you can see them stand out much more than when I talk. So earlier when you walked in, I was playing a very, very high-pitched frequency, up around 19.7 kilohertz. Okay, so it's just barely registering on the graph right there. As I speak, my voice doesn't even come close to that. Okay, no human voice could ever make a frequency that high pitch. If I turn it up a little bit, you should see that peak kind of grow, hopefully. A little bit. You can see it getting a little louder. Can anybody hear anything now? I hear a little clicking. That's my speaker doing something weird. That's not really the sound. But it's a very, very, very soft sound. I'll do that again in a second. But as I start to bring it down, you'll definitely hear it. But I'm going to back the volume down a little bit. So let me bring it down to something I think everyone can hear. Just over 3 kilohertz. Okay? It's 3,196 hertz. So if I play that, make sure we're not too loud. That's a sound that I think probably everyone can hear. As I start to compress the sound wave more, what happens is the frequency is getting higher and higher pitch. So now this is up around 6,000, a little over 6,000 hertz. Higher pitch, but I think still still low enough frequency that everyone can hear it. Anybody that couldn't hear that? All right, so let's go up to around like 10,000 hertz or 10 kilohertz. So much higher. Anyone that couldn't hear that one? All right, let's go up to 14,000 hertz. Anyone that lost that frequency? No? And I can still hear that one too, up to 14. Let's try 16. Okay. Anyone that couldn't hear that one anymore? Yeah, couldn't hear it. Yeah, I can't hear the 16. I hear like a... No, actually, I don't hear anything like that. Even if I turn it up a lot louder, probably won't hear it. Higher pitch frequencies are harder to hear. That's the most annoying sound you've ever heard? Yeah. Yeah? It gets worse. So let's go up to... I'm not going to jump as much this time. I'm going to try to go to 17,000.
I can hear that.
You can still hear it?
I can't hear that one.
Can't hear that one. Yeah, I couldn't hear 16, so I can't hear that one.
There's no way you're ever hearing that.
So now I'm playing the frequency when you guys walked in.
One of those old ones in the
Yeah, sometimes you hear a TV make noise, like a really high-pitched noise. It's kind of like the sound you just heard. And that's the sound that nobody said they heard earlier.
I can hear it.
You can see that it's just barely registering. It's under the 0.02 line. If I back the frequency down, lower pitch frequencies are easier for us to hear. So if I start to back it down without even changing volume, you'll just start to hear it better, and you should see that peak start to slide to the left and probably go up a little bit as well. So let me just... So I'm sliding it to the left, and now it's definitely above the 0.02 line, but I didn't change any volume. Now you can see it's off the screen. Okay? It's just the way frequency works. Okay, and then we can kind of go in the opposite direction. We can play some lower pitch sounds. So it's a lower, much lower pitch tone, but nowhere near really the lowest we can go. So let's try just under 100. So what's happening now is it's starting to turn into more of a vibration, because that's what sound is. It's just really air vibrating. And if we go low enough, I should probably just go to the computer. So it's a little lower, but let me go over here. The lowest tone that I can play, because of the limitation of the speaker, is about 45 hertz. Okay, so if I play that, set both of them on 45, you can see the wave looks very stretched out. It's so stretched out we can't even see a full cycle of it on the program. About 45 hertz. It sounds about like that.
It's like a few persons that can type.
And that frequency, or different objects in this room vibrate at different frequencies. It's called resonance. So, for example, have you ever seen someone break like a piece of glass by playing a really loud sound? Like if you had a wine glass or something, and you run your finger over the top, you hear that frequency that it makes. If you can record what that frequency is, like using a program like I have, and then play that exact frequency very loud, that would eventually cause the glass to shatter. It would break. It's not like every piece of glass in that area would break at the same time, because everything vibrates at a different frequency. So in this room, when I get up around 57, 58 hertz, there's certain things in the ceiling that start resonating at that frequency. When I play this one, there's something vibrating a little bit, but as I make the frequency higher, you'll definitely hear, you'll hear something else vibrating. So maybe. So there's something. There's that. So as I go up, all of a sudden you started to hear, I don't know if it's the lights or the vent or something, but something starts to resonate with that frequency because that's the frequency that that thing wants to vibrate at, and I'm playing that vibration frequency very loud. So, low pitch sounds. As far as the low pitch, in the other room, they definitely can hear that very easily. The high-pitched sounds don't travel well. So if you're standing right outside the door and I'm playing a really high-pitched sound in here, you're not going to hear it well. Just high-pitched sounds don't travel through walls, but low-pitched sounds do. So there's different properties of sound waves. And we'll talk a little more about some uses, some military uses with sound, and some cell phone stuff if we have a little time. All right, so since we are stretching and compressing the graph, we're changing the period. Okay, the normal period is 2 pi, or 360 degrees. That's the amount of time it takes for the graph to go up, go down, and back up. So in that case, it was as long as that green line. But for the red one, the amount of time to go up, down, and back up is only as long as that red line. And if I remember right, that was a quarter of the green one. So what we're going to figure out is what would be a formula to find out how big the period is now. Originally it was 2 pi from here to here. Now it's shorter. It's a quarter of that. So how do we figure it out? Basically, to find the length of a new period, you take the original period, which is 2 pi, and you divide it by whatever number you put in front of x. So in the example I just had, I think it was 4. The period, or the length from here to here, is 2 pi divided by 4. It's 1/4 the length of the original. Okay? But everything is based off 2 pi, because that's the original, and then you divide it by whatever's in front. So this is the second type of question you're going to see on the test. That is not a graphing question. Okay? It's going to give you an equation and just ask you to find the period. Okay? So we just have to use the formula up above. Okay, so let's do the first one. Okay, so the formula for the period is 2 pi divided by, and this symbol just means the number that's in front of x. So what number is in front of x here? 2. 2 pi divided by 2. The period of sine 2x is pi. Is that bigger than the original period or smaller? Smaller. The original period was 2 pi. This period is 1 pi. Okay, what does that really mean? If you go from 0 to 3.14, you will get 1 full cycle. Before, you had to go from 0 to 6.28. It's 2 pi. Okay. Now it's half the size. Okay, so it's compressed. We would hear that as a higher pitched sound. Any questions on that? The mistake that some people make here is they say the period is 2. No. 2 is just the number in front of x. 2 is just the number you fill in there. So you still have to fill the number in and then simplify it. Don't just say the period is the number in front of x. Okay, that's just the w looking thing. Okay, let's try cosine 5x. Brady, how would I write my period for cosine 5x?
2 pi over 5.
Yes, 2 pi over 5. So the period here is the original period divided by 5. Another way to say that is it's compressing by a factor of 5 because it's now 1/5 as long as it was. Okay, questions on that one? Okay, let's try this one. Sine of 1/4 x. Right, so Abby, how would I set up my formula to find the period of sine 1/4 x?
You need 2 pi over 1/4.
Yeah, I'm just going to make it as 2 pi over 1. You can always put a number over 1 if you want. The reason I made the top a fraction is because the bottom is a fraction. Now, we can't leave that. We got to do that out. So, Cassandra, when I have a fraction divided by a fraction, how do I do that?
With the bottom
Yep. Flip the bottom and then
multiplied.
multiply it. Exactly. Keep the top the same. Flip the bottom and multiply it. So, Tanner, what's 2 pi times 4?
8 pi.
8 pi. Which is much bigger than the original period. The original period was 2 pi. The answer here is 8 pi. How much bigger? 4 times bigger. Okay, we would hear that as a lower frequency sound. We stretch the wave out. Okay, any questions on that? So there'll be some problems just like that on the test. Jordan, what if I did this? What would be the period of 1/4 sine 1/4 x plus 3? Anyone have a thought what the period would be now? Yep.
8 pi.
8 pi. I didn't change it. So you have to be able to know that the plus 3 does not affect the period at all. Has nothing to do with it. You could even put a 2 in front. That has nothing to do with it. Only number that affects the period is what's in front of x. You can ignore everything else. Okay, so how do we find the 5 key coordinates for a period change? Well, that's what I'm going to show you right now. First of all, let's figure out what's going to stay the same. Ryan, if we're stretching and compressing horizontally, which values are not going to change? The y's are not changing. We're going to do stuff horizontally. That's the x's. So the y's stay the same. Unfortunately, the y's are the easiest numbers to work with. So today we don't get to work with the ones, the zeros, and the negative ones. We have to work with the fractions with pi. Okay, so to find the new x's. There's a couple ways I can show you to find the new x's. I'm only going to show you one way. Out of the 2 ways I could show you, sometimes one way is better, it's faster. Sometimes the other way is faster. It kind of depends. But I'm going to show you how to do it this way. So when we write down our original table, what is the first x coordinate in sine or cosine? First x is always what? It's always 0. Now let's say you double 0. Stretch it. If you double 0, what do you get? You still get 0. What about if you compress 0? Let's make it smaller, take half of it. What do you get? You still get 0. So the first coordinate is always going to be 0, no matter how much you stretch or compress it. Kind of think of like a bungee cord around like hook it around on a hook. If you pull it, the hook that's on the, like hooked on a nail or something, that part doesn't move. That part stays right where it is. It's everything after that that stretches and compresses. That's kind of like this idea. The 0 is going to stay right where it is. It's not going to stretch or compress at all. Everything after it is going to stretch or compress. All right. So, it's going to start at 0. The next thing we want to figure out is where it ends. Basically, I want to figure out the distance from there to there. How do I figure out the length of the period? What's the formula to do that? Well, Colton?
Is it 2 pi
Over, yeah, they call that Greek letter omega. It looks kind of like a W. So to find the length of the period, to find the new period, you use that formula. So that formula will tell you the distance from there all the way to there. It'll give you the coordinate, the x value of the coordinate. Okay, so using the formula I just showed you, that gives you the end of the period. Now, we're going to find 5 points here, just like we've always done. The x values that we've had all week have a pattern to them. When you draw the x values, or if you plot the x values, they're all what? When you graph your x values. What did we say when you label an axis? You have to make sure that everything is always what? Okay. How about just when you label any axis in general? If you ever want to label an axis, you have to make sure that if you were trying to teach someone how to number an axis, what's something you can't do? If you, sure, Austin?
You gotta space them evenly.
You have to space them evenly. Right? We said you've got to make sure that you space things evenly. So the other 5 points are going to be spaced evenly between the 2 we already have. So I have the beginning, I have the end. What point would it make sense to find next, do you think, that would be spaced evenly between what I have right there? The middle. We're going to find the one in the middle. Okay. If you have 2 numbers and you want to get the one in the middle, what do? 2 numbers, okay? You got 2 numbers and you want the one in the middle. How do you find it?
Subtract the small and the bigger.
So like if I had a 90 and an 80, and I want to know the number in the middle of those 2, if I subtract 90 minus 80, I get 10. That's the range.
Add them together and then divide by the number of numbers.
Okay, add them together and divide by the amount of things you added. And what's that called? You're right. Does anyone remember what that's called? Yeah?
Mean.
Yeah, the mean. Exactly. It's the average. So if you want to find the one in the middle, you're going to average the first and the 5th x coordinates. So just find what's right in the middle of the first one and the last one. And now we can find the 2nd and the 4th, kind of doing the same thing. Caitlin, now that I have the 3rd, how would I find the 2nd?
Find the average of the first and the third.
Right, because when you find averaging, you're putting things right in the middle. You're spacing things evenly. That's what an average is. It's exactly in the middle of 2 things. So to find the 2nd coordinate, you're going to average the 1st and the 3rd. And then we have to finish up. with the fourth coordinate, which is going to be the average of the third and the fifth. So if you mess up finding the fifth coordinate, you messed up everything. Okay? Because the third coordinate is the average of the first and the fifth, and if the fifth is wrong, then the third is wrong, and you're going to use the third for everything else. So just be careful as you go through it. Okay, so we'll try a few examples of making the table for a period change and doing the graph, and then we'll see how much time we have left. Okay, any questions on the steps to find the coordinates for a period change? Okay, let's try an example. Okay, so our first example is going to be y equals sine 2x. Let's look at sine 2x. Step one. Now we know all the transformations. We have to identify which one out of the four this one is. So Nathan, which transformation is this? Yes, you got it. What are we studying today? What's the name of the section?
I don't know that either. I don't write down the names.
Someone tell them what we're doing today? We're doing period changes. All right, so we're doing period changes. So period change. My next question now, questions get harder, affects which axis? Pacey, does the period change affect the x values or the y values?
X.
It's going to affect the x's. So all the x's have to change. That means the y's stay the same. Carissa, what are my y values for sine?
0, 1, 0, negative 1, 0.
Okay, so we got those. Now we're going to take and find our new x's. Jamaica, what did I say that the first x value always is when you do a period change?
Stays the same.
Stays the same, so it stays as, I gotta put a number in there.
Oh, was it like 0?
Yep, stop right there, you're good, don't say anything else. 0. Okay, the first x value, the first x coordinate is 0. Okay. Once we get the first one, then we get the fifth one. Alan, how do I get the endpoint formula for how we do that?
It's E equals 2 pi over W.
And what is that in this case? 2 pi divided by 2. So t just stands for the length of the period. I don't know why they use t, it's what they use. So the period here is pi. So this graph is going to start at 0. It's going to finish its cycle at pi. Now we got to find some points in between to figure out the curvature. Okay, we've got 0, we've got pi. First, last. Now we can get what's in the middle. How about, Lexi, how do we get the third x coordinate, which is in the middle of the first and the fifth?
Take the average of pi and 0.
Yeah. Just take 0, add it to pi, and divide it by 2. That's how you average. You add the two things up and divide by 2. So Brady, what do I get for an average when I do that? How much?
Is it 2 over pi?
No, pi is in the top, and the 2's in the bottom.
So it's pi.
Pi over 2. And when you average something with 0, you just take half of it. That's why if you got, let's say you got a 70 for a test grade, and you got a 0 on the next one, it's very easy for me to get your average. I just take half your grade. So every time you get a 0, when you average two things, it just makes it cut in half. Okay? So using that idea, what's halfway between 0 and pi over 2? Yep. Yep, pi over 4. If you want to think in degrees, pi over 2 is 90, pi over 4 is 45. If it doesn't make sense how she got pi over 4, just do it out. 0 plus pi over 2 divided by 2. Well, this is the kind of situation that Cassandra told us about earlier. You're dividing a fraction by a fraction. Flip and multiply. Straight across. Pi times 1, 2 times 2. Okay, middle one. Okay, let's average and see what we get. So we've got pi over 2 plus pi. And just to avoid having to flip it later and multiply by a half, I'm just going to flip it right now. Because I know I'm going to divide by 2, so I'm just going to end up flipping it and multiplying by a half in the next step. Okay, what's wrong with trying to add these up? Pi over 2 and pi. We have a problem. Yep. We don't have a common denominator. So before we can add them up and then take half or divide by 2, we need a common denominator. Luke, what's my common denominator?
2.
2. So I'm going to double what's in the top, get 2 pi, double what's in the bottom, and I get 2. 1 pi over 2 plus 2 pi over 2, 3 pi over 2. But you still have to take half of it. We haven't done that yet. So Lauren, what's half of 3 pi over 2? So to multiply fractions?
Half of 3 though.
No, you don't take half of 3.
We're multiplying?
You're multiplying straight across.
So 3 pi over 4.
3 pi over 4. Now I said there's always a pattern. If you look at that, it doesn't look like there's a pattern at all. Yes, there is. That's 0 pi over 4, 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4. We've just reduced it as we went, so you don't see the pattern. But that's your table. Okay, so you can still look for a pattern, just like everything else, if that helps you. Okay, questions on the table? All right. These are nicely spaced. 0, 45, 90, 135, 180. We have a mark every 45 degrees. Okay, so use those to label your axis. You don't have to label 0. I know 0 is the axis. So we have pi over 4, pi over 2, 3 pi over 4, and pi. Okay, it's a little squished because I have it zoomed out. But. Okay, highest value is 1, lowest is -1. For today, that will never change. Okay, and now graph your points. 0, 1, 0, -1, back to 0. Everything looks nice and symmetrical, looks good. Questions on how we sketch that? Okay, as always, since we're changing our scale, you're not necessarily going to see the graph look very squished because I've changed my labels. Okay. All right, so that's our first one. Let's look at this one. Cosine 1/4 x. All right, so Nathan, I'm coming back to you. What kind of transformation is that?
Same one we just did.
Which is?
The, what was that? I don't even know.
Someone help him out? What kind of transformations is that?
Period change.
That's a period change.
What?
Coming back to you. Write it down. Here. All right, so cosine 1/4 x is a period change. What values stay the same? Yep. The y's. Unfortunately, y's are super easy to work with. We don't get to work with them. 1, 0, negative 1, 0, 1. Make sure you copy the y's from the cosine table, not the sine table. If you get them from the sine table, you just lost half the points. Okay, first x value, Ethan, is always
0.
0. First x value is always 0. So now we know where we start. We have to figure out where we stop. Okay. What's the formula to find out where we stop? Yep. Yeah, go ahead, Mom.
2 pi over 0. Right? Wait, hold on.
2 pi over
Oh, 1/4.
1/4. I'm not going to go through that again because we already did it right here. 2 pi divided by 1/4 is 8 pi. So now we know where we're going to end. Okay, 8 pi. So I've got the beginning, I've got the end. What's the middle coordinate? Yep,
4 pi.
4 pi. The second coordinate? 2 pi. And the fourth coordinate? 6 pi. So sometimes the averages work out nice. This is an example where the method I showed you is faster. Okay. And that's it. So now we just make our sketch. And we're good. So we've got 2 pi, 4 pi, 6 pi, 8 pi. So we're drawing it out much farther than we normally have to. Normally we get to stop at 2 pi. We've stretched this graph way out. 1, negative 1. I should have made my labels a little lower. I'm just going to draw through them. And my y's, 1, 0, negative 1, 0, 1. 1, 0, negative 1, 0, 1. And there's my sketch. Any questions on that one? All right, so let's look at the last one. Now, if you look at this one, you might be like, oh geez, now we have a pi in front of the x. And it might look like the numbers are going to work out to be bad. For this problem, the numbers are going to be the nicest numbers we've seen all week in any problem we've done. Okay. First thing we have to do is identify what kind of transformation this is. Nathan.
How's it going?
Good, how are you?
Good.
What kind of transformation is this?
I sure hope it's a period change.
It's a period change. So it's a period change because we've got multiplication inside the parentheses. Okay. If you put the multiplication in front, you just made it an amplitude change. All right. Hopefully by now we already know what stays the same. It's the y's. 0, 1, 0, negative 1, 0. The first x is always 0. So those 6 should be pretty quick. Now we got to do a little bit of calculations. I need to calculate where the cycle ends. To do that, I use my formula. So what's going to be my calculation I set up to find the fifth coordinate? Luke?
2 pi over pi over 2.
Yep. And since the bottom is a fraction, I'm going to make the top a fraction. 2 pi over 2. To divide those, we're going to flip and multiply. So we get 2 pi. The bottom, flip it, becomes 2 over pi. And when I multiply straight across, what's going to happen there? Yeah, Cassandra? It's going to come out to 4 pi over pi. And what is 4 pi over pi? Just 4. So the pi's cancel out. So now halfway between 0 and 4 gives me halfway between 0 and 2. And between 2 and 4? 3. So I told you the numbers in this table would be the nicest ones all week. So this is a problem that if you don't label anything on your axis, you wouldn't get any points off. Because I think reasonably you could go by 1s on the x-axis, and you could go by 1s on the y-axis. And it would work just fine. But I'll label it just because I have them. And we've got 0, 1, 0, negative 1, 0. 0, 1, 0, negative 1, 0. And there's your graph. That graph has been compressed a little bit. Normally we would have to go to 2 pi to get one full cycle. 2 times pi is 6.28. Now you're getting a full cycle before 6.28. You're getting it at 4. So it's been compressed a little bit. Not a lot. All right. Any questions on period change? All right. So let's take a look at just a couple different things with sound. The first one I want to show you, I can't demonstrate it, so I have a video for it. It's called an LRAD. Has anyone ever heard of that before? LRAD? It stands for Long Range Acoustic Device. And basically what it is it's like a spotlight for sound. So it's like if you aim a spotlight or a laser at a certain spot, it only goes in that direction. That's what it's designed to do. The light is very directional. Versus like the light bulbs in the ceiling here, they go everywhere. Right? Light the whole room, not just one spot. Well, the LRAD is a special speaker that directs the sound exactly in one spot. So if you're standing behind it, and the sound can't echo in a room, let's say you're outside, and you're behind it, you don't really hear it. You go over in front of it, and it's extremely loud. So it projects sound in one small area. Okay, and I'm going to show you a use for that. I'll show you a little clip on that.
Cheaper if I go pick it up.
In response to the terrorist attack on the USS Cole in October of 2000, American Technology Corporation created a device like no other. LRAD, the long-range acoustic device.
A wave of the future. A high-tech tool developed by the military. A high-tech sonic weapon.
Long-range acoustic device, or an LRAD.
The long-range acoustic device, or LRAD, is like an audio spotlight. When you're standing alongside of it or behind it, you can carry on a normal conversation, but get directly in its beam, and the sound becomes almost painful.
Because of its weight and size, the LRAD is easy to transport, easy to set up, and mounts almost anywhere.
Cruise passengers now, barely escaping that pirate attack.
We're learning more about that stunning pirate attack.
This magnificent cruise ship attacked off the coast of Africa by 21st century pirates.
The LRAD's usefulness was most recently demonstrated in November 2005 when pirates attempted to attack a cruise ship off the coast of Somalia.
It has 26 languages and about 100 different remarks, like put your hands on your head, or lie flat on the ground, or turn around and do such and such.
The system clearly enables us to enforce the Naval Vessel Protection Zone at all times.
The fact that an individual was informed of the reasonable consequences of his actions and continued to defy legitimate authority, they are personally responsible for whatever happens next.
Whether initiating communication or warding off unknown adversaries, the LRAD has proven effective more than 80% of the time and has saved countless lives in the process. From American Technology Corporation, LRAD, the long-range acoustic device.
So you saw some of the uses, like for riot control and just to disperse people, because it's a very loud sound. You couldn't hear it that well because the volume on the video is kind of soft. If I turn my volume back down, this is what the LRAD sounds like. So that's the frequency. That's a picture of what it looks like. So it's a little more complicated than a sine wave. But the point is, it's a sound that if you hear it loud enough, you don't want to be around it. And if you do decide just to stand in front of it, eventually it can damage hearing. It can cause permanent hearing loss because it's such a powerful speaker. Another thing you saw they can use it for is just to project messages, because they don't have to just play that sound. They can actually use it with a microphone and talk over the LRAD. So it's a nice way to communicate something very far away to someone if you need to for some reason outside. So that's the LRAD. I have another clip of showing like a show where they use it. For now, I'm gonna hold off on showing you that, but it's from a show called Rail Wars. I don't know if anyone ever watched it or heard of it. They use an LRAD on a helicopter, and the helicopter pilot explains what it kind of sounds like. It's basically an awful sound. And he can't really cover his ears because he's flying the helicopter, so he moves away from it. That's the thing about an LRAD. It's somewhat narrow. If you move 20 feet to the right, it's not going to affect you anymore, just like a flashlight. If I'm shining it at you, you move 20 feet one way, it's not going to be shining at you anymore. So it has kind of a narrow cone of effectiveness. But that's the point. It's very directional. All right, so the thing I'm going to show you is it's abbreviated DTMF. And it stands for dual tone, multi-frequency signal. Dual means two. So we're talking about two tones played at the same time. And that's basically how telephones work. Cell phones, house phone, the phone in this room. Whenever you press a button, you get two frequencies played at the same time, and it'll sound like that button. So let me show you the frequency for a 1. It's 1209 and 697. So if I play, first I'll play just the 1209. Doesn't really sound like a button on the phone. 697. I play that one. Okay, that doesn't really sound like a button on the phone either, but the combination of the two played together, now it sounds like a button on the phone. Everything that you hear on the phone, the dial tone, the ringing, busy signal, all of that stuff is just two frequencies played at the same time. I think this is the ringing tone, 440 and 480. And then it pulses. If you change one of those frequencies just a little bit, just go from 480 to 470, something doesn't sound right. And that would probably be off enough that a phone wouldn't interpret that as the right frequency. So what I can do is if I call my voicemail, it'll say like press 4 to enter your personal options, where I can change my greeting and all that stuff. Well, instead of pressing the button on my phone, I'm going to generate the frequency for it. And as long as I'm close enough, but I can be exact using this program, my phone will think I pressed the button and it'll go into the menu options. And then it'll say something like press star to exit. Because I'm kind of far from the speaker, I got to turn it up. And it also has to be pretty quiet, otherwise the phone won't hear the signal as well. So let me try it. I know it says press 4 to enter your personal options. So that's a 1209 and 770. So I'm just going to get that ready. That's probably loud enough, but I'll go a little louder. And as long as I have reception, this should work. So let's see.
Listen to your messages. Press 1 to send the message. Press 2 to check receipt of the message. Press 3 to change your personal options. Press 4 to disconnect. Press star. Personal options. To turn notifications on or off. Press 1 to change administrative options. Press 2 for clean or recorded name. Press 3 to change notification options. Press 4 to exit. Press star. You have 2 saved messages, main menu. To listen to
And then one more time, it'll
click
hit
1
this.
to send a message.
I gotta wait for it to
Press
stop.
2 to check receipt of a message. Press 3 to change to personal options. Press 4 to disconnect. Press star. Goodbye.
That's so cool.
So just by generating the right frequencies, the phone is thinking I'm pressing the buttons. Now, if I change 941 to 940, would it work? Probably. If I change 941 to like 921, no. It wouldn't quite be the right frequency that the phone wants to hear. And I could do the same thing with the wall phone, because that's a dial tone. I could just hold it up like this, and if I could generate the frequencies fast enough, because you only have a certain amount of time, you can't take 6 minutes to dial a phone number. If I could do it in like 20 seconds, I could call another room without pressing any buttons on the dial. So that's one use for frequencies. If we have class tomorrow, I'll show you some stuff with music, kind of some interesting YouTube stuff, and if not, then we'll just have our test on Friday.